What if you could step into a time machine right now and vanish into the past only to discover your own future self already standing there, waiting for you? This spine-tingling scenario isn't just science fiction, it's the famous Bootstrap Paradox, a real head-scratcher that physicists and storytellers have wrestled with for decades. Think about it. If you travel back and give your younger self the blueprints for a time machine, where did those designs originally come from? The answer loops back on itself endlessly, like a snake eating its own tail. And this is just one of the dizzying riddles hidden in the fabric of time itself. Time travel isn't just a playground for Hollywood. It's a deep, haunting question that's tugged at human imagination for centuries. Why? Because it confronts us with the ultimate what if. What if you could undo regrets, witness history firsthand, or peek at the fate of humanity? It's the stuff of dreams and nightmares. After all, even the tiniest change to the past could unravel reality as we know it. Yet scientists take these ideas seriously. Einstein's relativity opened the door to bending time. Quantum physics hints at parallel timelines, and cutting-edge theories suggest wormholes might be cosmic shortcuts. The line between science and speculation has never been blurrier. That's exactly why we're diving into 30 of the most mind-bending time travel theories today, from the eerily plausible to the gloriously outlandish. We'll explore how black holes might be natural time machines, why some physicists believe the future is already written, and whether you'd actually survive a trip through the fourth dimension. Along the way, you'll encounter paradoxes that twist logic, alternate realities where every choice spawns a new universe, and even the shocking idea that time itself might not exist. So buckle up, because by the end of this journey, you'll never look at a clock the same way again. The question isn't just can we time travel, it's what happens if we do. Picture this: a stranger hands you a leather-bound book of poetry so brilliant it changes your life. Years later, you travel back in time and give that same book to your younger self before it was ever written. So who truly created it? This is the Bootstrap Paradox in action, a dizzying loop where cause and effect collapse into endless circular logic. Take the most famous example. What if a time traveler handed Shakespeare a complete collection of his own plays before he wrote them? The plays would have no original author. They just eternally exist, trapped in a loop where Shakespeare both creates them and receives them from his future self. Even geniuses like physicist Stephen Hawking wrestled with this idea, calling it the most troubling paradox in time travel. But the implications go far beyond books and manuscripts. Imagine inventing a time machine using blueprints you found, only to realize those plans came from a future version of yourself traveling back to deliver them. The machine was never actually invented, it just exists because it always existed. This shatters our usual understanding of causality, where every effect must have a cause. The Bootstrap Paradox suggests reality might allow for things to spontaneously exist without origin, like a snake endlessly swallowing its own tail. Philosophers call this self-consistent time travel, where the universe forces events to neatly align, even if it means erasing the concept of beginnings altogether. Pop culture loves playing with this mind-bender. In the film 12 Monkeys, Bruce Willis's character hears a childhood memory of his own death, a moment he only experiences because he time-traveled to create it. The hit series Dark takes it further, where a pocket watch, a letter, even a character's very existence are all stuck in paradoxical loops with no clear start point. And in Doctor Who, the Time Lord famously says, "People assume time is a strict progression of cause to effect, but actually, from a non-linear perspective, it's more like a big ball of wibbly-wobbly, timey-wimey stuff." That playful line hides a profound truth. The Bootstrap Paradox reveals time might not flow the way we think it does. So what does this mean for free will? if the universe corrects itself to maintain these loops, ensuring Shakespeare always gets his plays or that you always build the time machine, are our choices real? Some theories suggest free will could be an illusion in a predetermined timeline, where every action is just fulfilling what's already written. Others argue these loops are proof of multiple realities, where each decision splinters off into new timelines, avoiding paradoxes entirely. One thing's certain, the Bootstrap paradox doesn't just bend time, it twists our deepest assumptions about reality itself. Now take the Bootstrap paradox and crank the stakes up to nightmare fuel. Welcome to the Grandfather Paradox, where time travel doesn't just twist logic, it threatens to erase you from existence entirely. Imagine stepping into the past and accidentally or intentionally killing your own grandfather before he has children. Without your parent being born, you could never exist to travel back in time, so how could you have committed the act in the first place? This isn't just a plot twist from Back to the Future. It's a genuine philosophical grenade that's been debated by physicists for nearly a century. Stephen Hawking famously used this paradox to argue time travel must be impossible, calling it nature's way of protecting history from chaos. But other scientists refused to accept such a tidy answer. Russian physicist Igor Novikov proposed the self-consistency principle, suggesting the universe would somehow prevent the paradox. Maybe your gun jams, or you miss the shot, or a sudden gust of wind pushes you off course. Reality, in this view, acts like a cosmic editor, trimming away impossible contradictions to keep the timeline intact. It's a comforting idea until you realize it implies fate controls your actions, stripping away free will like layers of an onion. Then there's the multiverse solution. Every choice spawns a new timeline. Kill your grandfather. You've just split reality into two branches, one where you never existed, and another where you're now stranded in an alternate past. This theory turns time travel into a high-stakes game of Russian roulette with infinite universes as the chambers. TV shows like The Flash love this approach, where altering history doesn't rewrite the original timeline, it fractures it, leaving characters to navigate the fallout of their meddling. Quantum physics even offers a sliver of support here, with experiments suggesting particles can exist in multiple states until observed. Could entire universes work the same way? But perhaps the most unsettling answer comes from theorists who argue the Grandfather paradox proves time travel only works if the past is already unchangeable. In this fixed timeline model, your trip back was always part of history. Maybe you were the mysterious stranger who scared your grandfather into moving cities, leading him to meet your grandmother. Your actions don't alter events, they fulfill them. This twists our gut instinct about cause and effect, suggesting free will might be a beautiful illusion. After all, if you couldn't change the past no matter how hard you tried, would time travel really be freedom or just a prison dressed in gears and clockwork? The Grandfather paradox doesn't just ask if time travel is possible, it forces us to question what reality would even look like if it were. Could multiple versions of you exist across splintered timelines? Does the universe have a built-in undo button for paradoxes? Or are we bound to a single, unshakable history, playing out roles written long before we were born? One thing's certain, if time machines ever appear, we might not be the ones controlling them. The past and the laws of physics could be holding all the cards. What if every choice you've ever made, from what you ate for breakfast to whether you took that job, didn't just shape your future, but literally split the universe into multiple versions of reality? That's the spine-tingling promise of the many worlds interpretation, a quantum theory that turns time travel into a cosmic game of choose-your-own adventure. Imagine Schrödinger's famous cat, both alive and dead in its box until someone looks inside. The many worlds theory says both outcomes happen, just in separate branching universes. Now apply that to time. Step into a time machine and you're not rewriting history, you're hopping onto a new branch of the infinite timeline tree. This solves time travel's nastiest paradoxes with elegant bravado. Kill your grandfather. That horror plays out in one universe, while in another you miss the train and never even meet him. The original timeline stays untouched, like a parallel highway you've simply exited. Quantum physicist Hugh Everett first proposed this in the 1950s, arguing that every quantum event spawns new realities. Drop a glass, one universe where it shatters, another where it bounces. The implications for time travelers are staggering. There's no need to worry about erasing yourself because every possible outcome gets its own world. Pop culture adores this idea. In Avengers Endgame, when the heroes mess with the past, they don't overwrite their present. They create splinter timelines where Loki escapes or Thanos vanishes. The video game Life is Strange lets players rewind time, only to discover their changes birth terrifying alternate realities. Even the classic Sliding Doors film shows two versions of Gwyneth Paltrow's life based on whether she catches a train. These stories hint at a profound truth. If the many worlds theory is real, time travel isn't about changing history, it's about surfing the multiverse. But here's where things get weirder. Quantum experiments already show particles existing in multiple states until observed. What if conscious observers, like time travelers, trigger these splits? Some theorists suggest every decision we make could be a quantum event, meaning you're creating new universes right now without even realizing it. The math checks out, but the scale is mind-numbing. An infinite number of yous living out every possible version of your life across countless dimensions. Critics argue this is less science and more metaphysical overkill. Why invent endless invisible worlds just to dodge paradoxes? Yet for time travel enthusiasts, many worlds offer something priceless: freedom. No grandfather paradoxes, no bootstrap loops, just an ever-expanding cosmos where every possible past, present, and future plays out somewhere. The catch: you can never go home again. That original timeline you left behind, it's now just one thread in a tapestry too vast to comprehend. So next time you regret a choice, take comfort. Somewhere out there, another version of you is living the road not taken. The question is, would you even recognize yourself if you met? Einstein's theory of relativity didn't just redefine gravity. It ripped open the possibility of time loops hidden in the fabric of the universe itself. These aren't sci-fi fantasies. They're called closed timelike curves, or CTCs, bizarre pathways where space-time bends so severely that you could travel forward in time only to circle back to your own past. Picture a hiker on a mountain trail that twists so tightly, they eventually stumble upon their own footprints from earlier in the journey. That's a CTC, a cosmic Möbius strip where cause and effect tangle into knots. The math behind this madness traces back to Einstein's colleague Kurt Gödel, who stunned the physics world in the 1940s by solving relativity equations that allowed for entire universes where time looped like a record on repeat. In Gödel's model, if you traveled far enough in a straight line, you'd eventually return to your starting moment, having literally gone around time. Einstein called these solutions disturbing, and for good reason. They suggested the universe might not have a single, linear history, but countless overlapping loops where events replay eternally. Then came Kip Thorne, the Nobel Prize-winning physicist who took CTCs from abstract equations to tantalizing plausibility. Thorne's work showed how wormholes, theoretical tunnels through space-time, could act as time machines if stabilized by exotic matter with negative energy. Imagine two ends of a wormhole, one on Earth, the other hurtling near a black hole where time slows to a crawl. Step through the moving end, and you'd emerge in Earth's past, creating a man-made closed time-like curve. The catch: negative energy remains purely hypothetical, and the slightest misstep could collapse the wormhole into a deadly singularity. Yet modern research refuses to let the dream die. Quantum physicists like David Deutsch argue CTCs might exist on microscopic scales, where particles briefly loop back to interact with their past selves. Even more radical is the self-healing universe theory, where time travelers attempting paradoxes create new branches of reality, like a river diverting around a rock, keeping the original timeline intact. Closed timelike curves force us to confront a chilling question: if time is a loop, is free will just an illusion? Or does the universe somehow edit out paradoxes, ensuring every event, even time travel, fits neatly into a preordained script? From Gödel's spinning universes to Thorne's wormhole blueprints, one thing's clear: the line between physics and philosophy has never been thinner or more thrilling. Imagine a cosmic drill spinning so fast it twists the fabric of reality itself. That's the heart of Tipler's Cylinder, a wild yet mathematically sound time machine proposed by physicist Frank Tipler in the 1970s. Picture an impossibly dense cylinder, stretching light years long and spinning at nearly the speed of light. According to Einstein's equations, this gargantuan spinning rod wouldn't just warp space, it would drag spacetime around it like taffy, twisting it into a closed loop. Travel around the cylinder in a precise spiral path, and you could end up arriving back at your starting point before you even left. The genius of Tipler's idea lies in its avoidance of black holes or wormholes. Instead, it relies on frame dragging, a real phenomenon where massive rotating objects like Earth tug spacetime slightly along with them. But Tipler's cylinder takes this to extremes. Calculations show it needs to be infinitely long to avoid ripping itself apart, and its mass would have to approach infinity to generate enough gravitational pull. That's where the theory hits a wall. Infinite density isn't just impractical, it's physically impossible with known matter. Even neutron stars, the densest objects in the universe, can't come close. Critics argue the cylinder is less a blueprint and more a mathematical curiosity, a what-if scenario that pushes relativity to its breaking point. But supporters counter that it's a crucial thought experiment. By exploring these extreme edges of physics, we uncover deeper truths about spacetime's flexibility. After all, Einstein's theories once seemed equally outlandish until black holes were proven real. The cylinder also raises philosophical riddles. If time loops around it, does that mean events along its surface replay endlessly? Could you interact with past versions of yourself, creating another flavor of the Bootstrap paradox? And here's the kicker: Tipler himself later admitted the cylinder might require negative energy to stabilize, the same elusive ingredient needed for wormholes. It's a reminder that even the most audacious time travel theories converge on the same cosmic roadblocks, yet the idea still captivates. In Arthur C. Clarke's novel Rendezvous with Rama, a massive alien cylinder exhibits eerie time dilation effects, and physicists still debate whether advanced civilizations could harness spinning cosmic strings, hypothetical relics from the Big Bang, to mimic Tipler's vision on a smaller scale. Maybe the cylinder isn't a practical time machine, but it's a dazzling testament to human imagination, proof that even in a universe of rigid laws, time might still bend to the right kind of spin. Bury a tunnel through the fabric of spacetime itself, and you might just have the ultimate shortcut, not just through space, but through time. That's the tantalizing promise of wormholes, those hypothetical cosmic tunnels beloved by sci-fi writers and physicists alike. Unlike black holes, which crush everything into oblivion, a stable wormhole could, in theory, offer a smooth passage between two distant points, or even two different moments in history. Picture a folded piece of paper with a pencil poked through it. The whole connects opposite sides instantly, bypassing the long journey across the surface. Now imagine one end of that wormhole orbiting a black hole where time crawls, while the other sits safely on Earth. Step through the moving end, and you'd emerge in the past, like walking through a door into yesterday. But here's the catch: wormholes, if they exist at all, would snap shut faster than a mousetrap the moment anything tried to pass through. That's where exotic matter comes in, a hypothetical substance with negative energy that could prop the wormhole open like cosmic scaffolding. Unlike normal matter, which gravity pulls inward, exotic matter would exert negative pressure, pushing outward to counteract the tunnel's collapse. The problem: we've never found a shred of this mysterious material. Quantum physics hints that tiny amounts of negative energy might bubble up briefly in a vacuum, but scaling that up to stabilize a wormhole would be like building a skyscraper out of soap bubbles. Even if we cracked the exotic matter puzzle, the challenges multiply. Any attempt to turn a wormhole into a time machine risks triggering catastrophic feedback loops. Imagine sending a signal through the tunnel to your past self, who then sends it back again. The signal could amplify infinitely, unleashing enough energy to vaporize the wormhole and possibly the universe. This blue screen of death scenario led physicist Stephen Hawking to propose the chronology protection conjecture, a cosmic fail-safe that might prevent time travel altogether. Yet the dream persists. Nobel laureate Kip Thorne, who advised Carl Sagan on the wormhole physics in Contact, calculated that a traversable wormhole would require the energy equivalent of compressing Jupiter into a single atom. Recent theories suggest quantum entanglement, where particles instantly influence each other across vast distances, might offer a backdoor to stability, weaving the wormhole's walls with subatomic threads that defy classical physics. From Einstein's equations to the wild frontiers of string theory, wormholes tease us with a vision of time travel that's mathematically possible yet maddeningly out of reach. They force us to ask, are we limited by the laws of physics or just by our imagination? One thing's certain: if these cosmic shortcuts ever become real, the universe will have rewritten the rules of the game. And the first person to step through might not just be visiting history, they could be changing it forever. Beneath the smooth expanse of the cosmos, there might be cosmic cracks so narrow yet infinitely dense, leftover scars from the Big Bang itself, that they could tear open corridors through time. These are cosmic strings, theoretical strands of energy thinner than an atom but stretching across the entire universe, each packing the mass of a mountain range into every inch. Picture a razor's edge slicing through space-time, warping everything around it like a bowling ball resting on a trampoline. Now imagine two such strings drifting past each other at nearly the speed of light. According to mind-bending calculations by physicist J. Richard Gott in the 1990s, their gravitational whirlpool could twist space-time so violently that it forms a closed timelike curve, a literal time loop where the future circles back to meet the past. Unlike wormholes or Tipler's cylinder, cosmic strings don't require exotic matter or infinite density. They're remnants of the universe's fiery birth, when space-time underwent phase transitions akin to ice crystals forming in freezing water. If they exist, their sheer density would warp time itself. Gott's breakthrough showed that two parallel strings moving in opposite directions would create a frame-dragging effect so extreme, a spaceship looping around them could depart after arriving, a paradox straight out of a time traveler's diary. The math checks out, but the engineering is pure fantasy. These strings would vibrate with the energy of quasar explosions, and getting close enough to harness them would mean surviving gravitational forces capable of shredding planets. The beauty and terror of this theory lies in its simplicity. No negative energy, no spinning cylinders light years long, just two rogue filaments from the dawn of time weaving a temporary bridge across ages. Sci-fi fans might recognize the concept from Contact, where Ellie Arroway's wormhole ride echoes Gott's ideas. Even more intriguing is how cosmic strings could solve the Grandfather Paradox without invoking multiverses. If the loop created by the strings is self-contained, your actions within it might be predestined, like a DVD replaying the same scene flawlessly every time. Step out of the loop and history remains untouched, yet skeptics highlight one gaping hole. We've never detected a cosmic string. Telescopes scan for their faint gravitational lensing signatures or ripples in the cosmic microwave background, but so far the universe keeps its secrets. Some theorists argue strings would have decayed eons ago, while others hold out hope that advanced civilizations, if they exist, might have already threaded time using these cosmic zippers. Whether relic or revelation, cosmic strings remind us that the universe might still hide shortcuts through time, written in the fine print of creation itself. And if we ever find them, the past might not be nearly as distant as it seems. You might not realize it, but your smartphone is constantly getting corrected for time travel, just not the kind you see in movies. Every time you use GPS to navigate, satellites orbiting Earth are adjusting for a bizarre fact. Time ticks slower for them than it does for us on the ground. This isn't a glitch, it's Einstein's special relativity in action, proving time dilation is real, measurable, and happening all around us. The faster you move, the more time stretches like taffy. At everyday speeds, the effect is minuscule, but crank it up to near light speed and the differences become staggering. Imagine two twins. One stays on Earth while the other rockets away at 99% the speed of light. Upon returning, the traveling twin might have aged only a few years, while their sibling could be decades older. This twin paradox isn't hypothetical. Cosmic rays strike Earth's atmosphere with such velocity that particles called muons, which should decay in microseconds, survive long enough to reach the ground. From their perspective, time slows dramatically, extending their lifespans like cosmic time travelers. But speed isn't the only thing bending the clock. Gravity does it too. Near a black hole like Interstellar's Gargantua, where gravity warps spacetime into a sinkhole, time crawls to a near halt. 1 hour on a planet orbiting it could equal 7 years back on Earth. Astronauts landing there might return to find their loved ones long gone, their own bodies barely aged. Einstein's general relativity revealed this chilling truth. Gravity doesn't just pull objects, it stretches time itself. Even Earth's modest gravity creates tiny ripples in time. Atomic clocks at sea level tick slower than those on mountaintops where gravity weakens slightly. Scientists must account for this when syncing time for global networks, proving relativity isn't just abstract math, it's woven into the fabric of daily life. The takeaway: time isn't the rigid, universal constant we assume. It's fluid, bending under the weight of speed and gravity. Whether it's satellites in orbit or heroes stranded near a black hole, the universe insists time is always negotiable. The real shocker: you're technically time traveling right now, just too slowly to notice. What if the universe itself conspires to stop time travelers from creating paradoxes? That's the spine-tingling promise of the Novikov self-consistency principle. A radical idea suggesting time travel might come with built-in guardrails. Russian physicist Igor Novikov proposed that any actions taken by a time traveler were always part of history, meaning you couldn't change the past even if you tried. Think of it like cosmic fate stepping in. Drop a billiard ball into a wormhole to knock its past self off course, and the universe will somehow ensure it misses or glances just enough to keep events consistent. The past isn't a fragile vase you can shatter. It's a locked puzzle where every piece already fits. This isn't just abstract theorizing. Picture a scientist attempting to send a message warning her younger self not to build a time machine. The Novikov principle insists the message would fail. Maybe the ink smudges, the paper burns, or she simply ignores it. The universe, in this view, operates like a meticulous editor, trimming away contradictions to preserve the timeline. Even seemingly chaotic events would subtly align to prevent paradoxes. In the film 12 Monkeys, Bruce Willis's character desperately tries to alter history, only to realize his actions were always part of what shaped it. His screams in the past already echoes in the future he came from. Critics argue this reduces free will to an illusion, a cosmic script where we're merely actors hitting predetermined marks. But supporters counter that self-consistency doesn't erase choice. It simply means our choices are woven into the fabric of time from the start. Imagine a novelist who crafts a twist where the hero's actions in Chapter 10 were always destined to happen based on Chapter 1. The character still makes decisions, they're just part of a larger, coherent narrative. The Novikov principle also offers a tantalizing solution to the grandfather paradox. Travel back to kill your ancestor and the gun jams or your aim falters not by accident, but because the universe enforces consistency. Some physicists take this further, suggesting quantum mechanics might naturally filter out paradoxical events like waves canceling each other out. It's as if reality has an immune system, rejecting timeline infections before they spread. So is time travel a locked room where every key already fits the lock? Or is Novikov's principle just a clever way to dodge paradoxes we don't yet understand? Either way, it forces us to confront a haunting possibility. If the past is unchangeable, then every moment, even our attempts to rewrite history, was always meant to happen. The universe, it seems, might have a stricter no-refunds policy than we ever imagined. Ever stepped on a bug only to realize your footstep was the very reason it crawled into your path? That's the predestination paradox in miniature, a cruel joke of causality where your attempt to alter history becomes the reason history unfolds exactly as it did. Picture this: you travel back to stop a pandemic, but your panic-driven warnings cause the very panic that spreads the virus faster. Or perhaps you try to prevent your parents' meeting, only to accidentally orchestrate their first encounter. This isn't just a twist from films like 12 Monkeys or Looper. It's a real philosophical grenade lobbed at our understanding of free will and determinism. The paradox gets its teeth from a simple, brutal logic. If time travel exists, then every event in history, including the time traveler's own actions, was always part of the timeline. No edits, no rewrites. In 12 Monkeys, Bruce Willis's character James Cole spends the film chasing a mysterious group he believes unleashed the apocalypse, only to discover his own childhood self witnessed the real culprits, a revelation that was always buried in his fractured memories. His entire mission didn't change the past, it cemented it. Philosophers call this causal loop determinism, where the universe operates like a sealed puzzle box. Every piece fits, even the ones you try to force. But could reality really work this way? Quantum physicist David Deutsch argues yes, proposing that any time travel-induced paradoxes would resolve into self-consistent events through quantum probabilities. Think of it like a river finding the path of least resistance. History might bend, but it won't break. Meanwhile, neuroscientists point to studies showing how human brains often confuse intention with action, making us feel like architects of events we merely witnessed. If time travelers are just actors in a pre-scripted play, their choices might be illusions, their rebellion staged. Films love exploiting this existential dread. In The Terminator, Kyle Reese is sent back to protect Sarah Connor, only to become the father of the future savior he was meant to defend. His mission didn't alter fate, it fulfilled it. Even ancient myths grapple with this idea. Oedipus tries to flee a prophecy that he'll kill his father, but his panicked flight leads him straight into the fatal encounter. The message is as old as time. Running from destiny might be the fastest way to meet it. So where does this leave free will? If every attempt to change the past was always part of the past, are we just puppets of time? Some theorists propose a chilling compromise. Free will exists, but only within the boundaries of what's logically consistent. You can choose to time travel, but the universe corrects your actions to fit the timeline, like a cosmic game of Tetris where every block snaps into place. Others suggest the predestination paradox only applies in fixed timelines, branches where reality refuses to fracture, enforcing a single, unshakable history. One thing's certain, this paradox doesn't just challenge time travel, it challenges our deepest notions of agency. If the future can reach back and shape itself through our actions, then every decision we make might be less about creating new paths and more about tracing ones already drawn. The past isn't a locked door, it's a mirror reflecting the choices we haven't realized we've already made. And that's the real mind bender, not whether we can change time, but whether time has already changed us. Quantum mechanics already defies common sense with particles that vanish, reappear, and exist in two places at once, but what if it also holds the key to time travel? At the subatomic level, reality plays by rules that make even the wildest sci-fi seem tame. Take quantum teleportation, where particles instantly transfer information across vast distances as if space and time don't exist. This isn't just spooky action at a distance, it's a phenomenon that hints at retrocausality, the jaw-dropping idea that future events can ripple backward to influence the past. The smoking gun for this temporal madness, the delayed choice experiment, a brain-melting test where physicists manipulate particles after they've already been measured. Here's how it works. Imagine shooting photons through a maze of mirrors, forcing each particle to choose whether to behave like a wave or a particle. But here's the kicker: scientists can retroactively change that choice by altering the experiment setup after the photons have already passed through. It's like voting in an election, only for someone to change the candidates after your ballot's been counted. The photons seem to know the future setup, adjusting their past behavior accordingly. Nobel laureate John Wheeler called this a great smoky dragon, where the tail, the future, bites the head, the past. Retrocausality isn't just a lab curiosity, it reshapes how we view time itself. If particles can be nudged by events that haven't happened yet, could larger systems, even consciousness, be subject to the same backward influence? Some theorists propose that quantum entanglement, where particles remain mysteriously linked across space, might also thread moments in time. Picture two entangled particles, measure one in the present, and its twin in the past instantly decides its state, as if your current observation reaches back to rewrite history. This isn't science fiction, it's the heart of the quantum eraser experiment, where erasing information in the present seemingly changes how particles behaved in the past. The implications are staggering. If retrocausality scales beyond the quantum realm, it could mean the universe is constantly stitching together cause and effect in both directions. Your decision to drink coffee this morning, maybe it was subtly influenced by your future self craving focus for an important meeting. Philosophers debate whether this undermines free will or simply reveals time as a two-way street we've only been walking in one direction. Quantum time travel doesn't require warp drives or black holes. It suggests the fabric of reality might already be threaded with tiny temporal shortcuts. While we can't yet send humans back in time, experiments keep proving that at the quantum level, the past isn't set in stone. It's a conversation between what was, what is, and what might yet be, all playing out in the subatomic shadows where time's arrow might just be a suggestion. Imagine the entire universe as a vast cosmic DVD, where every moment in time is etched onto its surface like a frame in a movie. Now here's the twist. What if our three-dimensional reality, the depth, the textures, even the flow of time, is just an illusion projected from this two-dimensional surface? That's the essence of holographic universe theory, a mind-melting idea suggesting the past, present, and future might not unfold in a straight line but coexist simultaneously like scenes stacked on a film reel. This isn't just poetic speculation, it's rooted in cutting-edge physics. The theory emerged from studying black holes, where scientists discovered that all the information swallowed by these cosmic voids isn't lost but encoded on their event horizons, the point of no return. Think of it like a prison tattoo inked onto the walls of a cell, holding every detail of what's inside. Extend this to the entire universe, and you get a staggering possibility. Reality, as we experience it, might be a grand projection from a flat, information-rich boundary at the edge of space-time. Time takes on a whole new meaning in this framework. If the universe is a hologram, then rewinding moments isn't about traveling backward. it's about accessing a different layer of the projection, like skipping to an earlier chapter on a Blu-ray. The past isn't gone, it's just not currently being played. This flips causality on its head. Your childhood, the dinosaurs, the Big Bang, they'd all exist eternally on the cosmic disk waiting to be accessed. Even the future could already be encoded, not as destiny but as potential frames in the hologram's library. Science fiction has flirted with this concept for decades. In The Matrix, characters jack into a simulated world where time can be paused or rewound, a crude metaphor for the holographic principle. More profoundly, the theory echoes ancient spiritual ideas like the Hindu concept of Maya, where reality is an illusion veiling a deeper truth. But here's where physics gets truly bizarre. Quantum experiments have found evidence supporting holography. When physicists measure the noise in the vacuum of space, it matches the static you'd expect from a two-dimensional surface projecting a 3D reality, like the fuzz on an old TV revealing the scan lines beneath the image. The implications for time travel, monumental. If the holographic principle holds, altering history might be less about changing events and more about editing the cosmic projection. Imagine a civilization advanced enough to manipulate the universe's source code. They could scroll through time like a video timeline, sampling moments without paradoxes. No grandfather paradoxes, no butterfly effects, just a cosmic cursor moving across the hologram's surface. Yet skeptics raise a crucial flaw. If we're living in a projected illusion, what's projecting it? The theory doesn't answer whether there's a higher reality behind the hologram or if the universe is somehow self-encoding. And while it elegantly solves the black hole information paradox, applying it to everyday time loops remains speculative. Still, the holographic universe theory forces us to confront a radical notion. Time might not flow at all. What we perceive as past, present, and future could be static slices in a grand cosmic slideshow. And the only thing moving is our awareness, flickering from frame to frame like a projector's light. So the next time you glance at a clock, consider this. Those ticking seconds might not be the universe's heartbeat, but just the hologram's playback speed, a cosmic illusion so convincing we've built our entire existence around it. What if you could cross the galaxy without breaking the speed limit of the universe? Enter the Alcubierre drive, a theoretical warp engine that doesn't push a ship through space, but instead bends spacetime itself like a surfer riding a wave. Mexican physicist Miguel Alcubierre cooked up this idea in 1994, inspired by Star Trek's warp speed but rooted in Einstein's equations. Here's how it works. Imagine your spaceship nestled inside a bubble of flat spacetime, while a ring of negative energy contracts space in front of you and expands it behind. You're not moving faster than light locally. You're cheating by shrinking the road ahead and stretching the one behind, surfing a ripple in the fabric of reality. The magic ingredient, exotic matter with negative energy density, a substance that defies gravity by pushing spacetime outward. While we've never observed such matter, quantum mechanics allows for fleeting glimpses of it. In labs, the Casimir effect shows tiny regions where empty space exerts negative pressure, hinting that nature might permit Alcubierre's wild idea on a cosmic scale. NASA Eagleworks lab even ran tentative experiments, attempting to detect microscopic warp bubbles using laser interferometers. The results were inconclusive but tantalizing, like catching the faintest whisper of a cosmic engine coughing to life. But the hurdles are galactic in scale. Early calculations suggested the drive would require the energy equivalent of converting Jupiter into pure negative mass, a power bill even Elon Musk couldn't cover. More recent studies slashed that estimate down to maybe the mass of a small moon, but skeptics still pounce. Some physicists argue the drive would vaporize anything inside the bubble with Hawking radiation or require materials sturdier than the laws of physics allow. Others fear the warp bubble could collapse catastrophically on arrival, unleashing enough energy to sterilize a solar system. Yet the dream persists because if the Alcubierre drive works, it rewrites the rules. Forget generation ships or cryopods. You could reach Proxima Centauri in weeks, watching stars streak past like raindrops on a window. And here's the twist: since space-time itself is moving, not the ship, relativity's time dilation effects might not apply. Travelers could return to an Earth where clocks ticked in sync with their journey, erasing the twin paradox's heartbreaking age gaps. The Alcubierre drive dances on the edge of possibility, equal parts revolutionary and reckless. It's a reminder that the universe's rulebook might have loopholes if we're bold enough to look for them. So while we're centuries from warping to Vega for lunch, the mere fact that physicists are crunching the numbers proves something profound. Light speed might not be the final frontier after all. Imagine a clock that ticks forever without ever needing to be wound. A machine that defies the second law of thermodynamics by cycling endlessly without losing energy. This isn't steampunk fantasy, it's the bizarre reality of time crystals, a quantum phenomenon so strange it rewrites the rules of motion itself. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals aren't just objects, they're phases of matter that oscillate in a repeating pattern not in space but in time. Picture a diamond where the atoms don't just arrange themselves in a lattice, but dance in an eternal loop, returning to their starting positions like celestial gears in a cosmic clock. The magic lies in their quantum choreography. Normal crystals like snowflakes or salt have atoms arranged in fixed spatial patterns. Time crystals add a temporal twist. Their atoms periodically flip state, say, from spin up to spin down, in a cycle that repeats indefinitely without energy input. It's as if you nudged a pendulum once and it kept swinging forever, untouched by friction or entropy. Scientists created the first time crystals in labs using chains of ytterbium atoms or nitrogen vacancies in diamonds, zapping them with lasers to initiate this self-sustaining quantum waltz. The result, a structure that ticks like a metronome locked in time's groove. But here's where it gets wild for time travel. Time crystals don't just model stability, they embody time loops on a microscopic scale. Their endless cycling mirrors the closed timelike curves of general relativity, where events repeat like frames in a film reel. Some theorists speculate that scaled-up time crystals could act as rudimentary time machines, creating pockets of spacetime where cause and effect stutter in predictable loops. Imagine a computer chip built from time crystal components. It might process information in a way where calculations from the future loop back to influence the past, enabling computations that defy linear logic. Yet scaling these quantum quirks to macroscopic reality is like trying to build a cathedral out of soap bubbles. Time crystals currently exist only in ultra-controlled environments near absolute zero, shielded from the jostling chaos of the warm, noisy world. Even a whisper of heat or interference collapses their delicate dance, and there's a deeper catch. Their oscillations are locked to quantum time, not the flowing seconds we experience. A time crystal's tick might be 1 billion times faster than a heartbeat, making synchronization with human-scale time akin to matching a candle's flicker to a supernova's pulse. The potential, though, is electrifying. If harnessed, time crystals could revolutionize quantum computing, creating memory that never decays or processors that exploit temporal loops for impossible calculations. For time travel, they offer a sandbox to test paradoxes, proof that at least in the quantum realm, the universe winks at the idea of eternal return. But for now, these crystalline chronometers remain fragile ghosts in the machine, whispering tantalizing hints that the arrow of time might just be a suggestion written in quantum ink. A single misplaced footstep in the Jurassic era could, in theory, redirect a river's course, wiping out a breeding ground for ancient insects that would have pollinated the plants feeding the ancestors of all mammals. Fast forward 65 million years, and that misstep might erase humanity from existence entirely. This isn't just poetic speculation, it's the butterfly effect in full, terrifying force. Chaos theory teaches us that in complex systems, tiny variations in initial conditions can snowball into wildly divergent outcomes, like a single domino toppling a galaxy of others. Meteorologist Edward Lorenz stumbled onto this truth in the 1960s when he rounded a decimal point in a weather simulation and watched the forecast spiral into unrecognizable chaos. His revelation, the flapping of a butterfly's wings in Brazil could set off a tornado in Texas weeks later. Now apply that to time travel. Step on a blade of grass in medieval Europe, and you might return to a present where your hometown was never built. The darker twist, unlike in films like Back to the Future, where Marty McFly's meddling visibly rewrites reality in real time, real chaos theory suggests you wouldn't even know what you'd altered until it was too late. The changes could take centuries to manifest, hidden in the fractal maze of cause and effect. Physicists call this sensitive dependence on initial conditions, but for time travelers, it's more like playing Russian roulette with history. This is where the butterfly effect collides head-on with self-consistency models like Novikov's principle. Chaos theory says every tweak cascades unpredictably. Self-consistency insists the universe corrects your actions to preserve the timeline. So who's right? Surprisingly, both could be. Imagine firing a bullet into the past. Chaos theory says that bullet's path could ripple into a hurricane of change. But self-consistency might argue you'd miss the shot, or the gun would jam, because your present existence proves the bullet never altered anything critical. It's the ultimate cosmic tug-of-war between determinism and chaos. Pop culture loves amplifying the butterfly effect's drama. In Ray Bradbury's A Sound of Thunder, a time traveler crushes a prehistoric butterfly and returns to a dystopian future where fascism reigns. The Butterfly Effect film franchise turns personal regrets into timeline catastrophes, where small childhood changes erase relationships or trap characters in nightmarish alternate lives. But these stories often ignore an uncomfortable truth. In true chaos systems, most minor changes would cancel themselves out over time, like waves smoothing sand. The real danger isn't stepping on a bug, it's interfering with linchpin events, rare moments where history teeters on a knife's edge. Kill a random Roman soldier and history might shrug. But nudge Caesar's assassin's blade a centimeter off course, that's when civilizations might pivot. The chilling takeaway: if time travel were possible, we'd need more than a moral code. We'd need a physics degree to navigate the minefield of unintended consequences. Every breath taken in the past could be a hurricane in the making, every touch a tectonic shift. The universe might not just be stranger than we imagine, it could be far more fragile. What if the past, present, and future aren't flowing like a river, but frozen like ice cubes in a cosmic tray, equally real and unchanging? This is the spine-tingling core of eternalism, the philosophy that time is a static, block universe, where every moment from the Big Bang to the heat death of existence already exists in a fixed four-dimensional structure. Think of it like a DVD where every scene is permanently etched onto the disc, but the laser of your consciousness only illuminates one frame at a time. Your birth, your first heartbreak, the last breath you'll ever take, they're all equally real, just elsewhere in the block. Einstein's relativity quietly smuggled this idea into physics. When he proved time slows near massive objects, he shattered the notion of a universal now. Two events simultaneous for one observer could be years apart for another. This means the present isn't a shared stage, it's a local illusion, like a flashlight beam crawling across a darkened mural. Philosophers took this further. If relativity treats time as just another dimension like space, why privilege the present? In Moscow, Napoleon's retreat is past. To a hypothetical observer near a distant quasar, it hasn't happened yet. Eternalism says all these perspectives are equally valid. The universe doesn't play favorites with now. Films like Arrival flirt with eternalism's eerie beauty. When Louise Banks learns the alien language, her mind unlocks the ability to perceive her entire life at once, seeing her daughter's future death while cradling her as a baby. Her experience mirrors how eternalists view time, not as a parade of vanishing moments, but a landscape where every hill and valley coexists. Even grammar hints at this truth. We say, Columbus sails in 1492, not sailed, as if the event still unfolds somewhere in the temporal tapestry. But if the future's already out there, does free will evaporate? Not necessarily. Eternalism doesn't demand predestination, just that all possible choices and their consequences are part of the block's topography. Your decision to read this script exists in the same fixed relation to your breakfast this morning as New York does to Los Angeles on a map. The difference: you experience decisions as active, but that might just be the DVD player's laser convincing you it's creating the movie as it goes. Critics argue eternalism guts life's urgency. Why care if your future suffering is already written? Yet poets have long found comfort in this view. Writing from prison, Boethius imagined time as a wheel where all events eternally coexist, offering solace that pain, like joy, is just one note in an unchanging symphony. For time travelers, eternalism is a loophole. Visiting the past isn't rewriting history, it's exploring a region of the block always there, like hiking a trail marked on an ancient map. The block universe doesn't just reshape time, it redefines existence itself. Death becomes not an end, but a location in the timeline you no longer visit. Regret transforms from "I should have acted" to "my other choices exist in branches I can't perceive." And the next time you glance at a clock, consider this: the seconds aren't passing. They're all still here waiting for you to catch up. Stephen Hawking once bet against time travel, not because he lacked imagination, but because the universe might have built in safeguards against it. His chronology protection conjecture argues physics conspires to prevent paradoxes, acting like cosmic bouncers turning time travelers away at the door. Think of it as nature's firewall. Just as your computer blocks viruses, the laws of physics might snuff out any event that could shatter causality. Hawking's smoking gun. The eerie absence of tourists from the future. If time machines were possible, he quipped, why aren't we drowning in historians snapping selfies with dinosaurs? The math behind this cosmic lockdown gets wild. General relativity permits closed time-like curves, those loopy paths where time folds back on itself, but quantum mechanics might slam the door shut. Imagine a time traveler's particle beam circling back to its origin. Quantum fluctuations could amplify into infinite energy, triggering a feedback loop so violent it would vaporize the wormhole or warp bubble before paradoxes occur. It's like microphones screech in a concert hall, the universe's way of turning up the gain until the system collapses. Hawking dubbed this the blue screen of death for time travel, where quantum effects crash the party before it starts. Yet some physicists suspect loopholes. Quantum entanglement, where particles influence each other instantly across distances, already flouts classical causality. Could entangled particles threading a wormhole stabilize it instead of destroying it? Nobel laureate Kip Thorne toyed with this idea, suggesting exotic matter might lubricate the timeline, smoothing out paradoxes before they rupture. Others point to retrocausality in quantum experiments, where measuring a particle seems to rewrite its past behavior, proof that at microscopic scales time's arrow might wobble. The debate boils down to whether chronology protection is a fundamental law or just engineering homework we haven't solved. After all, black holes seemed mathematically impossible until we found them littering the cosmos. Maybe time travel isn't forbidden, just fiendishly delicate, like assembling a watch in a hurricane. Until we crack quantum gravity's code, Hawking's conjecture stands as both a warning and a challenge. The universe might guard causality like a dragon hoarding gold, but that doesn't mean we can't sneak past while it's sleeping. What if time isn't a fundamental force of nature, but a trick of the mind, a collective hallucination we've mistaken for reality? This radical idea isn't just philosophy, it's a cutting-edge theory gaining traction in physics. Carlo Rovelli, the visionary behind relational quantum mechanics, argues that time emerges from relationships between events, like how temperature emerges from the chaos of atoms. Think of it like a movie. What we perceive as time's flow is just individual frames, events our brains stitch together. At the deepest level, the universe might not have a clock ticking in the background. There's only before and after, defined by interactions. A photon doesn't experience time as it zips across the cosmos. Neither does a particle trapped in a black hole's frozen horizon. Time in this view is local, elastic, and maybe even optional. The implications for time travel are staggering. If time isn't a river but a web of connections, journeying through it might not require bending some universal fabric, just rewiring those connections. Imagine a cosmic version of editing a spreadsheet. Change how events relate to each other, and you've effectively jumped timelines. Rovelli's work suggests that what we call past and future are just convenient labels for patterns we've observed. In a timeless universe, every moment exists in a vast network of causes and effects. A time traveler wouldn't be rewriting history, just navigating a pre-existing maze where every turn was always part of the design. This lines up eerily with quantum experiments where particles seem to decide their properties retroactively based on future measurements. If time is relational, then the future might influence the past as easily as the other way around. Indigenous cultures like the Aymara people of the Andes already conceptualize time this way. They see the past as lying ahead because it's known, and the future behind because it's unseen. Modern physics might be catching up to ancient intuition, but if time is an illusion, why does it feel so real? Neuroscientists point to how our brains construct narrative. Memories aren't stored like files in a drawer. They're reconstructed each time we recall them, with gaps filled by expectation. Your sense of a continuous you moving through time might be the brain's best guess at stitching chaos into coherence. Even entropy, the universe's tendency toward disorder, often cited as time's arrow, might just be a statistical tendency rather than a cosmic rule. So could we exploit this for time travel? Maybe, if time is relational, then altering relationships between events could, in theory, let us hop between them. The catch: you'd need to manipulate reality at a scale that makes wormholes look simple. Yet the mere possibility reshapes the debate. Instead of building a DeLorean, we might need to hack the universe's source code, rewriting the very definition of now. The wildest part: if time is an emergent illusion, then the question isn't, how do we time travel? It's, what exactly are we traveling through? Ever met someone who swears they remember Nelson Mandela dying in prison during the 1980s, even though history books show he lived until 2013? You're not alone. Thousands insist they've seen this exact false memory, along with other bizarre discrepancies like the Berenstain Bears being spelled Berenstein, or Darth Vader's iconic line in The Empire Strikes Back, changing from "Luke, I am your father" to "No, I am your father." These shared misrememberings aren't just quirks of the human brain. They're the backbone of the Mandela Effect, a phenomenon so eerie it sparked wild theories about reality itself glitching. Could these collective false memories be proof of accidental time travel or universe hopping? Some theorists argue yes, pointing to the multiverse as the culprit. Imagine a cosmic game of musical chairs where every decision spawns a new reality. But sometimes the boundaries between these worlds blur. If a large group of people suddenly shift from one timeline to another, they might carry faint echoes of the old reality's history, creating phantom memories of events that never happened in this version of the world. In this view, Mandela Effect sufferers aren't misremembering. They're refugees from a slightly different universe where the facts were different. Skeptics, of course, roll their eyes. Psychologists explain the Mandela effect through the messy way human brains store and retrieve information. Our memories aren't perfect recordings, they're reconstructions, vulnerable to suggestion and external influences. When millions see a misquoted movie line online or hear others mispronounce Berenstein, those errors can overwrite the original memory like a corrupted file. The more a false version circulates, the more it feels true, a phenomenon called confabulation. Even Mandela's death might stem from media coverage of his imprisonment in the 80s, blending with his actual passing decades later. Yet the multiverse camp fires back with unsettling examples that defy simple explanation. Take the famous Flintstones vs. Flintstones debate. Some people vividly recall the cartoon being spelled with 2 T's despite all evidence showing one. If it were just bad memory, why would so many independently misremember the same extra letter? Even stranger, there's no record of any official merchandise, books, or ads ever using the double T spelling. It's as if these people are recalling a timeline where the show was called Flintstones, but no trace of that reality exists here. The debate gets even weirder when quantum physics enters the chat. The many worlds interpretation suggests every decision spawns a new universe, meaning there is a reality where Mandela died in prison or the Berenstein Bears were real. Proponents argue that when quantum states collapse, residual memories from neighboring timelines might bleed through like radio static from a nearby frequency. This would explain why Mandela effects often cluster around pop culture. Art and media might act as anchors that tether shared memories across realities. But here's the spine tingler. What if the Mandela effect isn't about memory at all, but about reality itself being edited? Some researchers point to the Large Hadron Collider, theorizing that high-energy particle collisions might briefly puncture the fabric between dimensions, allowing fragments of alternate histories to seep into our world. Others whisper about CERN's infamous 2012 shutdown, coinciding with a spike in Mandela effect reports. Could science have accidentally nudged us into a neighboring timeline without realizing it? Whether you chalk it up to faulty neurons or cosmic glitches, the Mandela effect forces us to confront a haunting question: how much of what we know is truly set in stone? If thousands can misremember the same non-existent details, what else might be up for debate? The color of a stop sign, the inventor of the light bulb. The very laws of physics, in a multiverse where every possibility plays out somewhere, the line between memory and prophecy might be thinner than we think. After all, if reality can shift once, who says it won't shift again? Crossing the event horizon of a black hole isn't just a one-way trip to oblivion. It might be the ultimate time machine, bending the fabric of reality until the past and future spiral into a single, inescapable loop. Picture this: you're falling toward a black hole's edge where gravity stretches seconds into eons. Time slows so dramatically that while minutes pass for you, centuries might flicker by for the outside universe. Step across that invisible threshold, and you're no longer just in space, you're unmoored from time itself, trapped in a cosmic whirlpool where the laws of physics as we know them unravel. But here's the catch: nature fights back against would-be time travelers with a process as brutal as it is poetic spaghettification. As you approach the black hole's maw, gravitational forces tug at your feet harder than your head, stretching you into a human noodle. Atoms that once formed your body get pulled apart like taffy until you're nothing more than a stream of particles spiraling into the abyss. Even if you could survive this gruesome fate, the sheer tidal forces near the event horizon would rip apart any known material, turning your ship and you into cosmic confetti long before reaching the center. Yet theoretical physics offers a glimmer of hope. Some models suggest black holes might not be dead ends but backdoors to elsewhere or elsewhen. Enter white holes, the hypothetical opposite of black holes. Where a black hole sucks everything in, a white hole spews everything out like a cosmic fire hose. If black holes are drains in the fabric of space-time, white holes are the geysers. Einstein's equations allow for their existence, and if they're real, falling into a black hole might spit you out through a white hole into another time or even another universe. Imagine being stretched to your limits only to reboot in a distant corner of reality, your atoms reassembled like a puzzle solved by the universe itself. The math gets even wilder when quantum mechanics enters the chat. Some theories propose that black holes don't destroy information but encode it on their surfaces like a hologram. If true, your journey through might not be annihilation but transformation. The information that makes you could get scrambled like a cosmic hard drive, then rewritten somewhere or someone else. It's less time travel and more reality recycling, where the universe repurposes your existence in a form barely recognizable. Pop culture loves playing with these ideas. In Interstellar, Cooper's plunge into Gargantua doesn't kill him, it flings him into a tesseract, a higher dimensional space where time becomes a physical landscape he can navigate. And in the Event Horizon film, a ship's experimental drive creates a man-made black hole that doesn't lead to another place, but to a hellish alternate dimension. These stories tap into our deepest fears and fascinations, that black holes aren't just killers but gatekeepers of the unknown. But before you start plotting a black hole joyride, consider the sobering reality. Even if white holes exist, they'd likely be unstable, collapsing faster than you could exit. And the odds of emerging intact, let alone in a usable timeline, are slimmer than winning the cosmic lottery. Yet the tantalizing possibility remains. Somewhere in the universe's darkest corners, the keys to time itself might be locked inside the very monsters we've spent centuries fearing. The question isn't just whether black holes can take us through time, it's whether we'd ever want to risk the trip. What if death isn't the end, but a doorway to another version of you in a parallel universe? The quantum immortality hypothesis takes Schrödinger's famous cat, the thought experiment where a feline is both alive and dead in a box until observed, and applies it to human consciousness with chilling consequences. Imagine you're playing Russian roulette with a gun that has 1 billion chambers and only one bullet. Statistically, you'd almost certainly survive, but what if you pull the trigger and the gun fires? Quantum immortality suggests your consciousness wouldn't end. It would simply jump to a parallel timeline where the chamber was empty, leaving behind a universe where your body crumples to the floor. From your perspective, you'd always experience the miraculous survival, no matter how improbable. This isn't just metaphysical speculation, it's rooted in the many worlds interpretation of quantum mechanics. Every quantum event spawns new universes, meaning there's always a branch where the unlikely outcome occurs. For every fatal car crash or lethal illness, there's a reality where you barely escape, your awareness seamlessly shifting to that timeline like a film reel switching to an alternate take. Your loved ones in the original universe mourn you, but you keep experiencing existence, blissfully unaware of the branches where your story ended, the terrifying beauty. You'd never be able to prove it wrong because from your subjective viewpoint, you'll always be the version that survives. Critics argue this reduces consciousness to a cosmic game of musical chairs, with no mechanism explaining how awareness chooses which timeline to inhabit. Others point out that quantum effects rarely scale to macroscopic events. A bullet firing isn't a quantum superposition. But proponents counter with quantum suicide thought experiments. If a device kills you based on a quantum event's outcome, an outside observer would see you die, but you would only experience realities where the device misfired. It's like flipping a coin indefinitely. You'll always land on the side where you're alive to observe the result. The implications for time travel are eerie. If consciousness can hop timelines, then subjective time travel might already be happening, not through machines but through quantum branching. Every near-death experience could be a glitch in the matrix, a moment where you almost slipped into another version of reality. Some survivors report seeing alternate lives flash before their eyes, as if glimpsing the branches they narrowly avoided. Even aging could be a form of timeline drift, with each year anchoring you to realities where your body holds out slightly longer. From Schrödinger's cat to your own mortality, quantum immortality forces a brutal question. Are we all just prisoners of probability, forever trapped in the timelines where we happen to persist? Or is consciousness far stranger than we've dared to imagine, a flame that never extinguishes, only flickers between worlds? The scariest part isn't the theory's audacity, it's that we might never know until it's too late to tell. What if every particle in the universe has already completed its journey, not just forward through time, but backward too, like a cosmic boomerang? This mind-bending possibility lies at the heart of the Wheeler-Feynman absorber theory, a radical model where cause and effect dance in perfect symmetry. Nobel laureate Richard Feynman and his mentor John Archibald Wheeler proposed that particles don't just march obediently from past to future, they zigzag freely in both directions, their paths stitching together the fabric of reality like threads in a double-sided tapestry. Here's how it works. Imagine firing a radio signal into space. Classical physics says those waves radiate outward endlessly into the void, but Wheeler and Feynman flipped the script. They argued that every outgoing wave is perfectly matched by an absorber, a future event or object that catches the energy and sends an echo back through time. These returning waves cancel out the original radiation, creating the illusion that signals travel one way. It's like shouting in a valley where every sound wave bounces back in perfect sync, making your voice vanish the instant it leaves your lips. But beneath that seamless silence, information is racing both forward and backward along the timeline. The implications for time travel are staggering. If particles can zigzag temporally, then manipulating quantum systems might allow us to encode messages in these back-and-forth loops, like slipping a note into a cosmic time capsule that only opens in the past. Experiments with quantum entanglement already hint at this possibility. When two entangled particles instantly influence each other across vast distances, could one particle actually be responding from its future state? Some interpretations suggest yes, proposing that quantum weirdness might be evidence of time-symmetric physics in action. Skeptics argue this violates our everyday experience. If particles are bouncing through time, why don't we see coffee cups reassembling from shattered fragments or smoke rushing back into cigarettes? Wheeler-Feynman's answer lies in the statistical avalanche of the macroscopic world. While individual particles might dance freely through time, their collective behavior emerges as the arrow of entropy we recognize, like how a single water molecule could theoretically reverse course, but an entire wave crashing onshore never would. Yet the theory's elegance is undeniable. It resolves thorny issues in electromagnetism, like why light waves appear to radiate outward when the underlying math works just as well for waves converging toward a source. It also offers a fresh perspective on retrocausality, the idea that future events can influence the past. If you've ever had a gut feeling about an event before it happened, could that be your brain subconsciously detecting faint echoes from particles that already experience the future? From Star Trek's subspace communications to the real-world hunt for tachyons, hypothetical particles that move backward in time, Wheeler-Feynman's vision keeps inspiring physicists. Their theory whispers a tantalizing possibility. Time's arrow might not be fixed. It could be a two-way street with reality's traffic flowing silently in both directions, and someday we might just learn to read the signs. Deep in the cosmos, spinning faster than a blender on its highest setting, dead stars called pulsars flash with such metronomic precision they rival atomic clocks. These collapsed stellar cores, no larger than a city yet denser than the sun, shoot beams of radiation that sweep across space like lighthouse beams, pulsing with a rhythm so exact you could set your watch by them if your watch needed to keep time within a millionth of a second. What makes pulsars truly extraordinary isn't just their regularity, it's how their position in the universe's gravitational tapestry makes them natural timekeepers. The deeper a pulsar sits in a gravitational well, say, near a black hole, the slower its pulses appear to distant observers, warped by the same time dilation effects Einstein predicted. Now here's the tantalizing thought. If we could harness these cosmic strobe lights, could they become the ultimate GPS for time travelers? The idea isn't as far-fetched as it sounds. Pulsars already guide spacecraft. NASA's nicer experiment aboard the International Space Station uses pulsar X-rays to test autonomous navigation for future interstellar missions, essentially creating a galactic positioning system. Each pulsar's unique pulse pattern acts like a fingerprint, allowing a ship to triangulate its position in space with freakish accuracy. But what if we took this further? If time slows near massive objects, then observing a network of pulsars from different gravitational environments could theoretically let us map not just where we are, but when we are. Picture a ship's computer comparing the arrival times of pulses from a pulsar near a black hole versus one in deep space. The discrepancies could reveal how much local spacetime is stretched, effectively letting you calculate your temporal coordinates in the universe. Yet for all their precision, pulsars present a brutal engineering hurdle. We have no known way to control their time-bending properties. Unlike a wormhole or Alcubierre drive, where hypothetical technologies might manipulate spacetime directly, pulsars are fixed features of the cosmos. You can't reposition a neutron star to tweak gravitational time dilation on demand. Even if you could park a spacecraft near a pulsar to exploit its time-slowing effects, the radiation pouring from these objects would vaporize you long before you aged a minute slower. And here's the cruelest twist. The very time dilation that makes pulsars useful also distorts their signals. A pulse emitted every millisecond near a black hole might arrive stretched to intervals of years for a distant observer, hardly practical for navigation when your clock ticks slower than continental drift. Science fiction has toyed with pulsar-powered time travel for decades. In the Doctor Who episode The Pirate Planet, a planet-sized machine harvests pulsar energy to compress time and space. Real-world physicists like David Deutsch speculate that advanced civilizations might encode information in pulsar beams, not for navigation, but as a way to send messages across epochs, knowing the signals will persist for millions of years. Even if we never ride pulsar beams like temporal surfboards, their pulses may hold clues to time's fundamental nature. Some theories suggest quantum vibrations in pulsar cores could interact with hypothetical time crystals, creating microscopic loops where cause and effect stutter. Others propose that colliding pulsars might twist spacetime into temporary knots, opening fleeting portals to other eras. The dream of a pulsar time machine lies in the razor's edge between inspiration and impossibility. They're the universe's most perfect clocks, but for now, we're stuck watching them tick from the sidelines, decoding their flashes like sailors straining to read distant lighthouses through a storm. Perhaps one day we'll crack the code, transforming these celestial metronomes into engines for temporal voyages. Until then, they remain both a promise and a taunt, time measured to inhuman precision, yet always just out of reach. What if the ultimate time machine doesn't involve wormholes or warped space-time, but lines of code so precise they reconstruct history atom by atom? Welcome to digital time travel, the radical idea that we could simulate the past with such staggering accuracy that it becomes indistinguishable from reality. Imagine a supercomputer capable of modeling every particle, every gust of wind, every whispered conversation in 18th century Paris, all rendered in flawless detail. Step into this simulation, and you'd walk cobblestone streets thick with the smell of baking bread, overhear revolutionaries plotting in dimly lit cafes, even feel the chill of a winter morning in Marie Antoinette's prison cell. The past wouldn't just be studied, it'd be relived. This isn't pure fantasy. Right now, physicists run simulations of the early universe with jaw-dropping precision, tracing the formation of galaxies from primordial soup. AI reconstructs lost languages and predicts archaeological sites with eerie accuracy. The gap between modeling history and resurrecting it narrows daily. Philosopher Nick Bostrom's infamous simulation argument takes this further. If civilizations inevitably create hyper-realistic ancestor simulations, odds are we're already inside one. Digital time travel flips the script. What if we become the simulators, bending bytes to rebuild yesterday? But here's where the dream curdles into a nightmare of ethical quandaries. If you reconstruct 1920s New York down to the last fire escape, do you digitally resurrect real people, their thoughts, fears, and joys, or just hollow avatars? Neurologists estimate the human brain holds roughly 5 petabytes of data. To simulate a single person's consciousness, you'd need to encode every synapse, every flicker of subconscious bias. Would these digital ghosts have rights? Could they suffer? The moment a simulation achieves true sentience, historians become gods and tourism becomes tyranny. And what of paradoxes? Change a single variable, say, prevent a simulated Lincoln from attending Ford's theater, and the simulation veers from history into fantasy. Does that matter if it's just code? Tell that to the AI civilians in a digital world war, Roman II watching Dresden burn all over again. Games like Red Dead Redemption 2 already boast open worlds so lifelike players feel guilt over pixelated crimes. Scale that to a historical simulation and the line between education and exploitation blurs. Then there's the epistemological crisis. If we perfect simulated pasts, how would we know our own reality isn't someone else's simulation? It's the ultimate bootstrap paradox. A future civilization could be simulating us while we simulate their ancestors ad infinitum. Digital time travel doesn't just risk rewriting history, it threatens to unravel our grip on what's real. Yet the allure is undeniable. Archaeologists could stroll through vanished wonders like the Library of Alexandria. Students might debate Socrates in his own Athenian agora. Families could visit ancestors they never met, hearing stories in voices long silenced. The past, often locked behind glass cases and yellow diaries, would pulse with life again. Perhaps the answer lies in boundaries, simulating environments but not consciousness, or restricting access to prevent exploitation. Or perhaps, like fire or fission, this power isn't inherently good or evil, but a mirror for our own intentions. One thing's certain, if digital time travel becomes possible, we won't just be rebuilding history. We'll be forced to confront who we are when the past is no longer a distant country, but a sandbox waiting for our cursor. What if the key to time travel isn't metal or machinery, but the human mind itself? The consciousness time travel theory flips the script on traditional physics, proposing that our thoughts might be the ultimate vessel for jumping through time. Imagine meditating so deeply that your awareness detaches from the present, swirling backward to witness historic events or forward to glimpse possible futures. This isn't just mysticism, it's a concept with eerie ties to declassified government experiments. Take the CIA's Stargate project, a Cold War-era program that explored remote viewing, where trained operatives claimed to psychically spy on distant locations and even different time periods. One declassified report describes a viewer sketching a 5,000-year-old Mesopotamian temple with unnerving accuracy, despite having no prior knowledge of its existence. The theory hinges on a radical idea: consciousness might not be anchored to the present. Neuroscientists know our brains constantly construct our sense of now by stitching together sensory inputs with a slight delay, meaning we're always living a fraction of a second in the past. But what if, under the right conditions, that delay could stretch into minutes, centuries, or millennia? Advanced meditators in Buddhist and Hindu traditions describe states of timeless awareness, where past and future collapse into a single, vivid present. Meanwhile, quantum physicists like Stuart Hameroff suggest consciousness arises from microscopic vibrations in the brain's neurons, vibrations that might, in theory, resonate across spacetime like ripples in a pond. Skeptics dismiss these claims as hallucinations or lucky guesses, but anomalies persist. In the 1980s, artist Ingo Swann supposedly remote-viewed Jove's rings before NASA, a Voyager, confirmed their existence. Another Stargate participant described a Soviet submarine base in such detail that analysts cross-referenced it with satellite photos, only to find a near-perfect match. Even if you chalk it up to coincidence, the implications are staggering. If consciousness can access information beyond spacetime's limits, then time travel might not require bending physics, just rewiring perception. Modern tech aims to bridge the gap between mysticism and machinery. Brainwave entrainment devices use binaural beats to induce states akin to deep meditation, while experimental neurofeedback systems let users visualize their brain activity in real time, training them to slip into altered states at will. Some theorists speculate that these tools, paired with AI, could one day tune consciousness to specific moments in history, like dialing a radio to a distant station. The catch: without physical travel, you'd be a ghost in time's machine, able to observe but not interact, like a spectator trapped behind one-way glass. Yet the most haunting question remains: if consciousness can wander through time, how do we know it hasn't already? Déjà vu could be fleeting echoes of future memories bleeding backward. Precognitive dreams, like Abraham Lincoln's alleged vision of his own corpse, might be fragments of timelines briefly intersecting. Even genius breakthroughs could be whispers from future selves, like Nikola Tesla's claim that inventions appeared fully formed in his mind. The consciousness time travel theory doesn't just challenge our gadgets, it challenges our very sense of self. After all, if the mind can roam beyond the body's limits, then you might already be scattered across centuries, gathering pieces of a puzzle only eternity can solve. Deep in the void between galaxies, where stars are sparse and light seems to vanish, an invisible force holds the cosmos together: dark matter. We can't see it, touch it, or detect it directly, yet its gravitational pull shapes the universe on a colossal scale. But what if this mysterious substance isn't just cosmic scaffolding? What if it's the universe's best-kept secret for bending time itself? Enter the dark matter time portal hypothesis, an idea so bold it straddles the line between genius and heresy. Some fringe theorists propose that dark matter's elusive nature isn't just a quirk of physics, but a clue to its ability to warp spacetime in ways ordinary matter can't. Imagine pockets of dark matter acting like natural time capsules, where gravity twists so strangely that entering one could send you careening through centuries. Mainstream physics, of course, greets this idea with raised eyebrows. Dark matter's primary job in the Standard Model is gravitational glue. It explains why galaxies spin faster than their visible matter should allow, and how cosmic structures formed after the Big Bang. Most researchers assume it's just an exotic particle that barely interacts with light or ordinary matter, like a ghost passing through walls. But the dark matter time portal camp asks, what if we're missing its most spectacular feature? If certain dense clumps of dark matter warp spacetime more aggressively than black holes, they might create temporary bridges between eras. These wouldn't be wormholes in the traditional sense, but more like time eddies, regions where the flow of time churns back on itself, allowing brief windows for transit. Here's where the theory gets daring. Quantum mechanics allows for particles to tunnel through barriers they shouldn't classically overcome. Some speculate that dark matter could exploit similar loopholes, enabling macroscopic objects like a spaceship to tunnel through time under the right conditions. Picture a vessel plunging into a dark matter nebula, emerging seconds later only to find Earth cities replaced by ancient forests or futuristic megastructures. The hypothesis draws loose inspiration from the dark fluid theory, where dark matter and dark energy are two faces of a single dynamic substance capable of altering its properties. If that fluid can locally tweak the curvature of space-time, who's to say time travel isn't on the menu? Skeptics, though, wield Occam's razor like a scalpel. Without direct evidence of dark matter's composition, let alone time-bending abilities, the hypothesis leans heavily on speculation. Current detectors like the Large Hadron Collider and underground xenon experiments hunt for dark matter particles by looking for rare collisions, not temporal anomalies. And even if dark matter could distort time, the energy required to stabilize such a portal might dwarf the output of entire stars. As physicist Sabine Hossenfelder dryly notes, the universe isn't obligated to be interesting. Yet history has a way of humbling skeptics. Black holes were once deemed mathematical fantasies until we imaged one in 2019. Cosmic inflation sounded absurd until the cosmic microwave background confirmed its fingerprints. The dark matter-time portal hypothesis, however improbable, forces us to confront an uncomfortable truth. We've mapped less than 5% of the universe's content. The remaining 95% dark matter and dark energy might harbor phenomena beyond our wildest imagination. Perhaps the most tantalizing piece of the puzzle comes from an unexpected place: the human brain. Neurologists studying near-death experiences report patients who describe time dilation effects, watching their lives flash before their eyes in slow detail. Could this be a biological echo of dark matter's hidden potential, or merely the brain's frantic final act? Either way, the line between science fiction and physics grows thinner by the day. If dark matter truly holds temporal secrets, unlocking them wouldn't just revolutionize time travel, it would rewrite our place in the cosmos. Until then, the portals remain hypothetical, lurking in the shadows of the unknown, waiting for a brave mind to shine a light. Have you ever walked into a room and felt an eerie certainty that you've lived this exact moment before, down to the creak of the floorboards, the slant of sunlight, even the fleeting thought that flickered through your mind? Déjà vu might be more than just a glitch in your memory. It could be a crack in the facade of reality, a fleeting glimpse of a time loop you've already lived through countless times. Welcome to the time loop prison theory, the spine-chilling idea that we're not just moving through history, we're reliving it, trapped in a cosmic rerun where every laugh, every tear, every choice we make has already happened an infinite number of times. This isn't just the stuff of movies like Groundhog Day. Ancient cultures from the Greeks to the Mayans saw time as cyclical, a wheel turning endlessly through ages of creation and destruction. Modern physics flirted with the idea too, in the form of the Big Bounce theory, a twist on the Big Bang where the universe doesn't end in a cold, dark whimper, but collapses back into a singularity, only to explode outward again in an eternal cycle of rebirth. Each iteration would be nearly identical, with the same stars forming, the same planets coalescing, the same civilizations rising and falling. In this light, déjà vu isn't a misfiring neuron, it's a haunting echo of the last cycle, a whisper from a version of you that already walked this path. But how could a time loop even work? Enter the concept of closed timelike curves, solutions to Einstein's equations where space-time twists back on itself like a Möbius strip. If the universe is shaped just right, say, rotating at a precise, mind-boggling speed, it could create conditions where the future loops back to meet the past, locking history into an inescapable groove. Philosophers like Friedrich Nietzsche took this further with the idea of eternal recurrence, suggesting that if time is infinite and matter finite, every configuration of atoms must eventually repeat. You'd have no memory of past cycles, yet you'd be doomed to make the same choices again and again forever. The psychological toll of this theory is staggering. If true, every joy you've ever felt is fated to be felt again, and so is every loss, the first kiss, the last goodbye, the moment you tripped on the stairs in 5th grade. They're etched into the universe's script, unchangeable. Even your rebellion against this idea would be part of the loop, a predetermined act of defiance. Some thinkers, like the Stoics, found comfort in this, arguing that if life is cyclical, we should embrace each moment as sacred. Others, like quantum physicist Sean Carroll, counter that entropy. The universe's tendency toward disorder makes perfect repetition statistically impossible. Yet the eerie precision of cosmic constants, like the gravitational force being just right for stars to form, keeps the idea alive. What if these perfect conditions aren't luck, but evidence of an ancient loop refined over countless cycles? Pop culture obsesses over time loops for a reason. In Russian Doll, Natasha Lyonne's character dies repeatedly, forced to confront her trauma until she cracks the code of her existence. Dark weaves an entire town into a knot of intergenerational cycles where every attempt to break free only tightens the grip of fate. These stories tap into a deep existential fear. What if growth is an illusion? What if we're just shadows on the wall of a cave, acting out the same play for an audience of none? Yet there's a tantalizing alternative. What if the loops aren't identical? The cosmic forgetfulness theory suggests each cycle introduces tiny variations, like a record skipping slightly off groove. This could explain humanity's flashes of intuition, from Mozart hearing symphonies in his head to scientists stumbling onto breakthroughs in dreams. Maybe these aren't divine gifts, but leaked memories from a nearly identical past iteration where someone almost got it right. The time loop prison theory forces us to confront the ultimate question. Is freedom an illusion? Are we explorers forging new paths or actors reciting lines written by the universe itself? Whether physics or philosophy holds the answer, one thing's certain: every time you felt that uncanny pang of déjà vu, you've brushed against a mystery far stranger than coincidence. The next time it happens, pause, listen. That whisper in your mind might not be your imagination. It could be the echo of you from a time before time saying, "We've been here before." Picture stepping into the past and accidentally extinguishing your own family line, only to find yourself still standing there, utterly unharmed by the paradox you just unleashed. This unsettling possibility lies at the heart of the time traveler's immunity theory. The idea that those who journey through time might be shielded from the consequences of altering history. It's a concept popularized by shows like Doctor Who, where the Doctor casually walks through eras like a ghost immune to butterfly effects. But could there be a scientific basis for this kind of temporal invincibility? One compelling angle comes from quantum physics. If time travelers are somehow entangled with their original timeline tethered to it through quantum links, their personal history might remain intact even as the world around them reshuffles. Think of it like a boat anchored in a raging river. The water, the timeline, rushes and changes direction, but the boat, the traveler, stays fixed. Quantum biologist Simon Berkovich even proposed that consciousness itself could act as a temporal anchor, with the observer effect in quantum mechanics somehow freezing a traveler's personal timeline in place while the external world mutates. Then there's the biological argument. Our cells are constantly dying and regenerating, but what if time travelers' DNA carries some hidden mechanism, a chronomarker, that signals to the universe this life form is exempt from rewrites? Bizarrely, nature already has analogues. Certain bacteria like Deinococcus radiodurans can survive lethal radiation by instantly repairing their DNA, almost as if they're coded to resist temporal disruptions. If human cells could be engineered with similar resilience, or if evolution had secretly baked in a failsafe for temporal tampering, travelers might emerge from paradoxes unscathed. But the darkest twist comes from an idea called causal decoupling. Imagine time isn't a single thread but a braid of countless fibers. A traveler's actions could fray one strand, say, erasing a war from history, while their own strand remains knotted to the original version of events. This wouldn't just protect them, it might split their consciousness across realities. In Avengers Endgame, when Steve Rogers lives out decades in an alternate timeline yet returns unchanged, it hints at this chilling possibility. The traveler isn't immune because they're special, but because they've become untethered from causality itself. Critics, of course, scoff at these ideas. If travelers were immune to changes, why wouldn't every historical tweak spawn armies of paradox-proof mutants? And how could quantum effects scale to shield an entire body? Yet the theory persists, fueled by eerie accounts like those of time slip, witnesses people who claim to briefly visit the past or future, returning to find their memories intact despite chronological inconsistencies. Perhaps the most haunting implication isn't scientific but existential. If travelers are truly immune, do they become prisoners of their own unchangeable pasts, forced to watch as their meddling erases loved ones who never were? Or worse, if they're the only ones who remember the original timeline, does that make them gods of memory, sole keepers of lost histories? The time traveler's immunity theory doesn't just ask how we'd survive messing with time. It asks whether survival would be a blessing or the ultimate loneliness. What if every time you step into a time machine, you're not just bending history, you're hijacking someone else's timeline? The parallel universe merge theory proposes that true time travel isn't about rewriting your own past, but violently colliding with another universe's future. Imagine pressing a button to visit medieval Europe, only to realize you haven't traveled backward. You've laterally invaded a parallel world where the 14th century still exists alongside their version of the 21st. Your arrival doesn't just create ripples, it triggers a cosmic custody battle over which timeline survives the merge. This idea reshapes how we view classic paradoxes. Kill your grandfather. Under this model, you didn't erase yourself. You overwrote a doppelganger from another branch of the multiverse. Their consciousness vanishes as yours occupies their historical moment, like a cosmic game of musical chairs where only one version gets to keep existing. The brutal math of quantum mechanics supports this. Every decision spawns new universes, so perhaps time travelers aren't rewriting history, they're hopping between infinite pre-existing variants. The terrifying implication, every journey could be an act of existential theft, erasing untold versions of yourself across the multiverse. This might explain the Fermi paradox's eerie silence. If advanced civilizations discover time travel, the merge theory suggests they'd quickly realize it's ethically catastrophic, like playing Russian roulette with alternate versions of Earth. Picture a future where time tourism is banned, not because it's impossible, but because every trip risks overwriting entire civilizations. The lack of alien visitors wouldn't mean we're alone. It could mean every intelligent species that cracked time travel chose to self-quarantine rather than gamble with cosmic genocide. The merge theory finds eerie echoes in quantum experiments. When particles become entangled, measuring one instantly determines its partner's state, even if they're light years apart. Some interpretations suggest this isn't communication, but a temporary merge of possible realities. Scale that up, and time travel might involve forcing entire universes into similar superposition states, with only one timeline collapsing into reality afterward. It's less Back to the Future and more dark, where every journey leaves casualties scattered across forsaken branches of existence. Could this be why we've never met a time traveler? Not because they're hiding, but because the survivors of temporal mergers are astronomically rare. The ones who do appear, like the infamous John Titor, claiming to be from 2036, might not be hoaxers, but refugees from annihilated timelines, their original worlds erased by the very act of reaching us. The ultimate cosmic irony, time travel might exist, but using it destroys the evidence. What if time isn't a river we're swept along, but a room we could step out of entirely? The zero-time theory dares to imagine a state beyond past, present, and future, where every moment in history sits side by side like books on a shelf waiting to be opened. This isn't just science fiction, it's a concept that bridges ancient mysticism and modern physics in ways that redefine what now even means. Mystics have whispered about this timeless realm for millennia. In Hindu philosophy, Brahman is the eternal reality beyond temporal illusion, where all events, your birth, Caesar's assassination, the heat-death of the universe exist simultaneously. Medieval Christian mystics like Meister Eckhart described the eternal now, a divine perspective where time is swallowed up in eternity. Even indigenous Dreamtime traditions speak of a dimension where creation myths aren't just stories, but ongoing realities accessible through ritual. These aren't metaphors, but claims of direct experience. It's like catching glimpses behind the stage curtain of reality. Physics is now flirting with similar ideas through loop quantum gravity, a radical framework that suggests space-time isn't smooth and continuous, but woven from tiny, indivisible loops. At this Planck scale resolution, time might not flow at all. It could pixelate into frozen frames, like a movie reel where every frame exists at once until consciousness plays them in sequence. Carlo Rovelli, a pioneer in this field, argues that time emerges from quantum relationships, not the other way around. Strip those away, and you're left with a timeless quantum foam where the Big Bang and tomorrow's sunrise hover side by side. The implications for time travel are staggering. If zero time exists, accessing it wouldn't require moving through years but transcending them. Think of a librarian who doesn't walk through library aisles to find a book, but reaches directly into a catalog where every text is equally present. Experiments with quantum entanglement hint at this possibility. When two particles interact instantaneously across light years, they're not breaking the speed limit, they're bypassing time altogether. Some theorists suggest advanced civilizations might harness this by creating time crystals, structures that resonate in zero time like tuning forks vibrating outside chronology. But how would zero time feel to a human mind? Near-death experiencers often report entering a realm where their entire lives unfold at once, not as memories but as a sprawling landscape where childhood and old age coexist. Neurologists chalk this up to the brain's final fireworks, but what if it's a fleeting brush with timelessness? Even LSD and DMT trips produce eerily similar accounts of eternity immersion, where users claim to touch a dimension where all moments are equally real. Whether these are hallucinations or glimpses of deeper reality remains hotly debated. The zero-time theory doesn't just challenge how we travel through history, it questions whether "through" is the right preposition at all. If every moment is fundamentally here, then time travel might be less about engines and wormholes and more about learning to shift our perception, to see the universe not as a narrative but as a painting where every brushstroke exists at once. The past isn't behind us, the future isn't ahead. They're simply waiting for us to adjust our gaze. From the dizzying loops of the Bootstrap paradox to the spine-tingling implications of quantum immortality, we've journeyed through theories that don't just bend time, they shatter our very notion of reality. Who could forget the cosmic horror of the Grandfather Paradox, where erasing your own existence becomes a twisted logic puzzle? Or the many worlds interpretation, where every choice spawns a universe and somewhere out there, a version of you is living every path not taken. Then there's the holographic principle, suggesting our 3D universe might just be a shadow cast by a 2D cosmic projector, with time itself as nothing more than an illusion painted on the edge of existence. But perhaps the most humbling realization is how these ideas blur the line between science and philosophy. Eternalism whispers that the past and future are just as real as the present, while the Novikov self-consistency principle argues the universe might be a predestined script, editing out paradoxes like a cosmic copywriter. And let's not forget the chilling Mandela Effect, where shared false memories hint at timelines colliding or worse, glitching. Each theory forces us to confront the same unsettling question: is time a river we float on or a labyrinth we're hopelessly lost in? Now it's your turn. Which of these mind-bending ideas left you staring at the ceiling at 3 a.m.? Was it the thought of black holes as natural time machines, or the eerie possibility that you're already reliving your life in an endless loop? Drop your favorite theory in the comments. We're obsessed with these cosmic riddles, and we know you are too. And if you're craving more deep dives into the universe's wildest mysteries, hit that subscribe button. The fabric of reality has plenty of threads left to pull, and we're just getting started.